Okay, so we have seen how ordinary differential equations are classified broadly and how we can solve linear first order differential equations. We have given out the full prescription for the same. Right, so there is this topic of orthogonal trajectories, which is important, right, when we are dealing with families of curves, right? So often, so we saw, for example, in the case of first order differential equation, you get a free parameter for the general solution, right? And so that corresponds to a whole family of curves. So while a family of curves is of interest, there is another family of curves corresponding to a given family of curves, which is going to be orthogonal to this, which is also of interest. So in this lecture, we look at how such an orthogonal trajectory, a family of orthogonal trajectories, is how to think about it, and also how we can come up with a differential equation and work out this orthogonal trajectory given a family, right? So that's the topic for this lecture. Okay, so this is perhaps best understood with the help of examples, right? So you're given some differential equation and suppose it yields a whole family of curves. Now it's of interest to find a family of curves which are perpendicular to the first family, right? So how would we do this? So let's look at this example which I've already looked at. So if you take the differential equation x times dy by dx is equal to y plus 1, this gives us the general solution y equal to ax minus 1, right, which is actually a bunch of straight lines, right, where a corresponds to the slope of this straight line, and as you vary a, the slope of this straight line will vary, and you cover a whole family of such straight lines. Now if we want to find a family of curves which are orthogonal to all these straight lines, right, we would note that the slope of this orthogonal family which is orthogonal to this should be dy by dx should be equal to minus 1 over the slope of the first family. But for the first family we already know what the slope is. It's dy by dx is equal to y plus 1 over x. It's given to us. But if we want to find orthogonal trajectories, their slope must be dy by dx should be equal to minus x divided by y plus 1, right? So this is a familiar result from basic coordinate geometry. We know that if two curves intersect at right angles, then the product of their slopes must be equal to minus 1, right? So that's being used here, and so we have dy by dx is equal to minus x over y plus 1, and which is a separable differential equation. A very simple scenario that I've considered here, right? There are more complicated examples which you can perhaps work out as homework later on. So solving this, we get x squared plus y plus 1 the whole squared is equal to c, right? So this is a separable differential equation, very straightforward to solve. And so now once again we have a free constant c, which is so now we have another family of curves which is immediately seen to be a family of circles, and these circles are perpendicular to the straight line solutions obtained earlier, right? So it is instructive to plot all of these curves. I have collected together a bunch of representative samples of members of each of these families, and then I am plotting them all. So okay, so this is taking a while. There you go. So it looks something like this, right? So the family of circles are like here, and the center of all these circles is of course this point 0 comma minus 1, right? 0 comma minus 1, and all these straight lines also pass through this point 0 comma minus 1, right? If you put x equal to 0, y has to be equal to minus 1 no matter what the value of a is, right? So those are all these straight lines. So all of these straight lines with different slopes pass through this point, and these curves with different radii, right, they are all circles, right? The orthogonal trajectories for this particular the family of curves is the family of circles, right? So in general, this problem can be more difficult to solve. So let's look at another example where we are not given the differential equation, we are given a family, and then we are asked to find a family of curves which is orthogonal to the first family. So let's look at this example. So suppose you are given this family of parabolas y equal to cx squared, right? So the technique here is to first find a differential equation for the first family, and then self-consistently eliminate the constant which is there in here. So let's look at this example and then it will become clear. So we have dy by dx is equal to 2cx, right? So eventually we want to write another differential equation, dy by dx is equal to minus 1 over the slope of this, but this constant is not a convenient object to work with. We want to eliminate this constant itself, but what is this c? C is y over x squared. So dy by dx is equal to 2 times y over x squared into x, which is just 2 times y over x. So we have managed to write down a differential equation where there is no constant, right? So if you solve this differential equation, of course you have to get back the same solution and with this arbitrary constant, right? So now once you have brought your differential equation, you've got your differential equation for your given family of curves, the next step is to write down the differential equation corresponding to the orthogonal trajectories, which is just dy by dx is equal to minus 1 over the slope of the first family. So that's going to become minus 1 over 2y by x, which is minus x by 2y, right? So once you have this, we can this is straightforward again to solve. So it's a separable differential equation. You have minus 2y dy is equal to x times dx. So that gives you, on integrating, you get x squared plus 2y squared is equal to a constant, right? So now you have a family of ellipses, right? So this family of ellipses are going to be are the orthogonal trajectories for your family of parabolas, right? In the first example, we saw that for this family of straight lines, we got a family of circles as the orthogonal trajectories, but for this family of parabolae of this kind, we are going to get a family of ellipses like specified here. Okay, so that's all for this lecture. Thank you.